Welcome to week 4 of linear algebra. This week we'll be doing chapter 2 on matrices. You're already familiar with matrices and how they relate to systems of linear equations. And so the first section, chapter 2.1, the space of matrices, is pretty much a review what you already know. So let's get right to it. The space of matrices, and here is my notation for the set of all M by N matrices over field K. Let V be capital M sub little m comma N over K, set of all M by N matrices. Then the matrices form a vector space over field K with the usual normal definitions of matrix addition and scalar multiplication. We know that a general M by N matrix A looks like what you see to the right here. A11 through A1n all the way down to A sub M1 to A sub Mn. A sub ij is the ijth entry of A. We denote the ith row of A by A sub I, and we denote the jth column of A by A superscripted J. Now, let us let A be an arbitrary M by N matrix, and then we want to define the transpose of A. So let's look at that. Let A be M by N matrix, okay? Then the matrix B, whose entries are simply BJI, where BJI equals AIJ, is an N by M matrix called the transpose of A. So the transpose of A equals B. The transpose of a matrix is where we simply interchange the rows and columns of the matrix. We just swap them out. So that's what we mean by the transpose of a matrix. Next, we define what does it mean for a matrix to be symmetric. A matrix A is symmetric if it equals its own transpose. That is, if the transpose of A equals A. All right? Now, let's suppose that our matrix A is square, N by N, square matrix. If A is, we say that A is diagonal, if all non-zero entries are on the diagonal and zeros below the diagonal and zeros above the main diagonal. You might write it as A equals diag, A11, A22, A sub NN. And then, of course, you know what the identity matrix is. The identity matrix is the diagonal matrix with ones on the main diagonal and zeros above and below the main diagonal. Then there's a couple of more definitions here. A matrix A is upper triangular if all of the non-zero entries are on or above the main diagonal. You might see it depicted this way, where you have the matrix with the diagonal line and the asterisk above it for non-zero entries, and the 0 below it for the 0 entries, and vice versa. A is lower triangular if all of the non-zero entries are either on or below the main diagonal. And there's how it's depicted with the diagonal line and the asterisk below it and the 0 above it. And so that's really all I have to say about section 2.1, but to make it a bit more interesting, I do want to look at a few exercises here. In particular, want to look at exercises 5, 6, and 10. Exercises 5, 6, and 10. All right, let's look at exercise 5 here on page 27, 28. If A and B are m by n matrices, show that the transpose of the sum of A plus B equals the transpose of A plus the transpose of B. It's very intuitive. All right, so let's just use our notation for the ijth entries. Let A be Aij, let B be Bij. All right. Then the jith, that is the transposed entry of transpose of the sum, is Aij plus Bij. But the transposed entries, jith entries, of transpose A is Aij, and of transpose B is Bij. And so they're equal. So that means the transpose of the sum is equal to the sum of the transposes. Now, later on, when we get to the chapter on inner product spaces, we're going to have another way of proving these same results here on 5 and 6. Number 6. If C is a scalar, show the transpose of CA equals the scalar C times the transpose of A. Well, again, we're using our ijth entry notation. A is Aij, okay? All right. And the transpose Bji equals Aij. All right. So let's look at it. And that means the transpose of Ca is simply C Bji. But on the other hand, C times the transpose of A is C times Bji. But then we can rearrange the parentheses there and put the parentheses to the left of C. So we have C Bji, but what's that? The line above says that's equal to the transpose of Ca. So we're done. It's very simple. And again, later on, we'll have another method of proving it, which is just as simple as this one is. And then finally, there's something else that's very important. Exercise number 10 says, show that for any square matrix A, that the matrix A plus transpose A is symmetric. And we'll see that this is important later on as we get farther in the course. All right, it's very simple. Again, it's just using the definitions of transpose. So on number 10 here, we have a square matrix, n by n. It doesn't matter whether A is symmetric or not. We know that A plus the transpose of A is symmetric. Now first we see a longer way to look at it with entries, and then at the bottom of the page I do a short one-line way to look at it. Again, let A be the matrix with Aij entries. Then the ijth entry of A plus transpose A is Aij plus Aji. And on the other hand, the jth entry of A plus transpose A is the reverse, Aji plus Aij, but those are equal. So the transpose of A plus transpose A equals A plus transpose A. That is, the transpose of A plus transpose A equals itself, namely A plus transpose A. Or look at the bottom there. Do it this way. So we've already proven in exercise number 5 that the transpose of the sum equals the sum of the transposes. So the transpose of A plus transpose A equals transpose A plus the transpose of the transpose of A equals the transpose of A plus A. It's very simple to see that if you transpose the transpose of A, what are you doing? You're interchanging the ijth entries, and then you're simply swapping them back where they were. And so you get the same matrix when you take the transpose of the transpose. Now, it's a simple result, but you'll see how important it is later on. Now, next, I want to look at the exercises on page 28, exercises on dimension. 1 through 9, they're all very important. I did not assign any of these for turn-ins, but I want to look at them in the video and in class. The exercises on dimension. Look at the first one. What is the dimension of the space of 2 by 2 matrices, and give a basis for that space? Okay. So we claim that the dimension of the space of 2 by 2 matrices is 4. All right. Of course, we know that a 2 by 2 matrix has 4 entries, and a basis for the 2 by 2s consists of elementary matrices. Now, remember that we know what an elementary vector is, the vector that has 1, 1, and all other entries are 0. Well, the same definition would apply to a matrix. An elementary matrix is a matrix that has only one entry that's 1, and all other entries are zeros. And so the notation is the basis for the 2 by 2s would simply be E11, E12, and then E21 and E22. For example, E11 is the 2 by 2 matrix that has a 1 in the 1, 1 entry, and then zeros in the other entries, etc. And then more generally, number 2, what is the dimension of the space of M by N matrices? Well, you simply multiply M times N. Just like for the 2 by 2s, 2 times 2 is 4. So, for example, the 3 by 4 matrices would have dimension 12. 3 times 4. So m times n, and a basis for the m by n matrices, as you see, consists of, you start row by row, E11, E12, dot, 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 to E1n, E21, E22, dot, 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 E2n, dot, 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 all the way down the last row, E sub m1, E sub m2, dot, 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 to E sub mn. And so there are m times n of those elementary matrices. All right, look at number 3. What is the dimension of the space of square matrices of all of whose components are 0 except possibly diagonal components? That is, diagonal matrices is what's under consideration. And it's very clear that the dimension of the square diagonal matrices is simply n. Why? Because there are n entries on the main diagonal, and the 0 entries do not contribute anything to the basis for the space. Now, it did not ask for a basis there, but I can put one in. The basis would simply be E11, E22, dot, 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 through E sub nn. That would be it. And there's n of those. Okay? Now look at number 4. More challenging. What is the dimension of the space of n by n upper triangular matrices? Again, remember, the upper triangular matrices are the matrices where the only 0 entries are below the main diagonal. The non-zero entries are either on the main diagonal or above the main diagonal. Now, all the zeros below the diagonal, they don't contribute anything to the basis for that space. The basis will consist of elementary matrices corresponding to the number of entries that the matrix has on the main diagonal and above the main diagonal. So that basis would be the set of elementary matrices Eij, where I is lesser or equal to j, and they run from 1 to n. I lesser or equal j takes care of the entries on the diagonal and above the diagonal. Now, how many entries are there? Well, there's n times n plus 1 divided by 2. Now, you might recognize that from Calculus 2 when you look at infinite series, sequences and series. The sum of the first n integers, 1 plus 2 plus 3 plus 4, dot, 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 up to n, is n times n plus 1 over 2. Now, think about it, for example. Just suppose you have, let's say, 3 by 3 matrices. How many entries are on the diagonal? 3. How many entries are above the diagonal? 3. Of course, 3 and 3 is 6. But if n is 3, then you got there what? 3 times 4 is 12, divided by 2 is 6. So for the 3 by 3 upper triangular matrices, it would have dimension 6. And the elementary matrices are, EIJ, I less or equal to j, running from 1 to 3. There's 6 of them. Okay? Look at number 5. What is the dimension of the space of 2 by 2 symmetric matrices? That is, the 2 by 2s, where A equals its own transpose. Now, certainly, in a basis for the 2 by 2 symmetrics, we're going to have E11 and E22, but we're only going to have 3 matrices in this basis. And the third one is the sum of E12 and E21. So there's 3. Okay? Now, more generally, looking at number 6, what is the dimension of the space of symmetric n by n matrices? And it's going to be the same as that of the n by n upper triangulars, namely n times n plus 1 divided by 2. And a basis for the symmetric square matrices consists of, you've got the EII's tacked on the n there, I1 to n, there's n of those. But then we have also running from 1 to n with I strictly less than j, EIJ plus EJI. So there are n times n plus 1 over 2 of those. And I might illustrate a specific example in class. Now, look at number 7. What is the dimension of the space of diagonal matrices? Well, that's very straightforward, isn't it? The diagonal matrices, the non-zero entries, are on the diagonal. And how many entries are on the diagonal? Simply n. So the dimension of the diagonal matrices, square matrices, is n, and a basis consists simply of the EII's, or I equal j, right? I running from 1 to n. Finally, numbers 8 and 9. Number 8, let V be a subspace of R2. What are the possible dimensions? Well, if it's trivial, it's consisting only of the 0 vector, it has dimension 0. If it's a line, it has dimension 1. If it's the whole space, it has dimension 2. Very simple. And number 9, if V is a subspace of R3, then it can either have dimension 0, 1, or 2, or 2, or 3. So it could be trivial, it could be a line, it could be a plane, or it could be all of R3. All right, so that would conclude that particular section. And we can go ahead and look then at linear equations 2-2. This is going very rapidly. Section 2.2, systems of linear equations. And so we know that we start out with an m by n matrix A, and let B1, B2, dot, 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 through B sub m be scalars. Then a system of m linear equations in n variables, x1, x2 through x sub n, looks like a11 x1 plus a1n xn equal b1, all the way down to am1 x12 plus amn xn equal b sub m. But we like to write these in a shorthand notation. So let A be the matrix of coefficients, and let capital B be the M vector, lowercase b1, b2 through b sub m. Then in shorthand, we always know we can represent it as AX equals, I meant to say capital B there, all right, represents the linear system. Also, you can represent it in the following very important way, and we use this representation in proving theorems. Using the superscripts to represent columns, and then the variables x1 through xn, a system of linear equations can be written as a linear combination of the variables with the columns of the coefficient matrix. x1 a superscript 1 plus x2 a superscript 2 plus xn a superscript n, the columns of A, equal to the column vector B, where A superscript j, again, is the jth column of A. All right? We say that a system of linear equations, AX equal B, is homogeneous if the B vector is equal to 0. Again, that's supposed to be a capital B there. If the B vector is 0. Or in other words, a system is homogeneous if you're looking at the linear combination of the columns of the coefficient matrix equal to the 0 vector. And using that notation, we immediately see then that the columns of the matrix are linearly independent if and only if x equal a 0 vector is the only solution to the system AX equals 0. In other words, the columns are linearly independent if and only if the trivial solution is the only solution to the homogeneous linear system. And on the other hand, the columns of the coefficient matrix are linearly dependent if and only if the homogeneous linear system has at least one or more non-trivial solutions. That is, if and only if there exists a non-zero vector x with AX equal the 0 vector. And that's very important in proving theorems. Okay? And so we have theorem 2.1, which I simply state and look at a one-line proof, theorem 2.1. Let AX be 0 vector, homogeneous system of equations, of m equations in n variables. Now, if n is greater than m, that is, if the number of variables is greater than the number of equations for a homogeneous linear system, then AX equals 0 has non-trivial solutions. And the proof goes back to theorem 3.1 in chapter 1, where if the dimension of the space is M and N is greater than M, then A1 through AN are linearly dependent. That is, when you have more vectors than the dimension of the space, then those vectors are linearly dependent. So we know now that for a homogeneous system, if there are more variables than there are equations, then it does have non-trivial solutions. Really, it actually has infinitely many solutions. Okay? All right, and then theorem 2.2, we have the following. Look at the non-homogeneous system, AX equal B, all right? But let it be a square system, that is M equals N, okay? Now, if the columns of A are linearly independent, then AX equal B has only one unique solution. Okay, let's see the proof of this theorem. Okay, again, we want to write the system using linear combinations of the columns of A. x1, a1 plus x2, a2, dot, 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 plus x sub n, an equal b. Now, since the columns of A are linearly independent, they form a basis for Kn because there's n of them. Okay? Remember the theorem in chapter 1 that says if the dimension of V is n and you have n linearly independent vectors, then they form a basis. So the columns of A are a basis, but now B is a vector in Kn. Okay? So that means there exist unique scalars x1, x2 through xn in K with x1, a1 plus x2, a2 plus dot, dot, dot plus x sub n, a sub n equal b. Hence, there's only one unique solution. Okay? And our homework for turn-in is on page 31, exercises 1 and 2. Exercises 1 and 2. I may look at 3 and 4 in class. And then finally, in chapter 2, section 3, we have matrix multiplication. I think I'm just going to do one long video for chapter 2, since it's so short. Now, matrix multiplication is a little more involved than matrix addition and multiplying matrices by scalars. And you know that, but let's remind ourselves how to multiply two matrices. Now, in general, we know that matrix multiplication is not always defined. It's only defined when the inner dimensions are equal. We'll see that momentarily. But now, the matrix multiplication is defined in the context of dot products. So let's start out by simply recalling dot products in Kn. All right? So let A, B, and C be vectors in Kn, and let X be a scalar. All right? Let A be the ordered n tuple, A1 to AN, and B is the ordered n tuple, B1 to Bn. Then remember, we looked at this in week 1. The dot product is simply the sum of the products of corresponding entries, A1, B1 plus dot, dot, dot plus A sub n, B sub n. And we have the three properties, SP1, SP2, SP3. The dot product is commutative. A dot B is B dot A. Number 2, the dot product is distributive across addition. And number 3, scalars go in and out wherever you need them to be. Now, we're going to look at another property called strict positivity and then non-degeneracy. Now, notice that for Kn, or in particular for Rn, the real numbers, for Rn, okay, if A is in Rn, then A dot A is non-negative, okay? And if A is not the zero vector, then A dot A, which is A squared, is strictly positive because one of the AI squares would have to be strictly positive. That's properties called strict positivity. So the vector space Rn has the property of strict positivity. However, for most applications that we deal with, strict positivity is more than we need. It's not necessary. Instead, we use another property called non-degeneracy, and I call this one SP4. SP4 says that if A is in Kn, and in particular, suppose that K is the complex numbers, and here's the definition of SP4. If A is in Kn and A dot x equals 0 for all x in Kn, then it must be the case that A is the zero vector. In other words, we say that the vector space is non-degenerate with respect to the dot product. A vector A in Kn is non-degenerate if and only if its dot product with all vectors is 0. In other words, if the zero vector is the only vector whose dot product with all vectors is 0. That's non-degenerate. So if there were a non-zero vector where you could say that its dot product with any vector is 0, then it would not be non-degenerate, it would be degenerate. That would mean that, it degenerates to 0. Okay? Now, let's define matrix multiplication. Matrix multiplication. Let A be M by N, and then let B be N by S. Notice that the number of columns of A is equal to the number of rows in B. Then the product, A times B, is the M by S matrix, where the ijth entry of AB is the dot product of the ith row of A with the jth column of B. That's the easy way to write it. The ith row of A dot product with the jth column of B, or at the bottom of the page, you can write it as the summation. K goes from 1 to N, A sub ik times B sub kj. But more easily, it's just the ith row of A times the jth column of B. All right? Now, I'm just going to mention some properties now for distribution and associative property. I'm going to mention these without proving them. Suppose A, B, and C are matrices and X is a scalar. Assume the following matrix products exist. Theorem 3.1 says that matrix multiplication is distributive across addition. A times B plus C is AB plus AC. And scalars go in and out wherever you want them. And theorem 3.2 says that matrix multiplication is associative. And I really don't care to go through the proof of those results. I'd rather look next at what do we mean by a square n by n matrix having an inverse. A square matrix is invertible or non-singular, has an inverse if there exists a square matrix B such that AB equals BA equals the identity. And we claim that whenever a square matrix has an inverse, that its inverse is unique. That is, it only has one inverse. It doesn't have two or more. And again, remember, we prove something's unique by supposing it's not unique. Suppose there's another one. Suppose C is another inverse of A, where A times C equals C times A equals the identity matrix. And then we have a one-line proof to show that B equals C. Well, B is B times the identity, which is B times AC, and then rearrange the parentheses, BA times C, but what's BA? It's the identity. And the identity times C is C. So the inverse, when it exists, is unique, right? So B is called the inverse of A, and it's denoted by A inverse. So now again, when the inverse exists, we don't know how to find it. Well, we do know how to find it by using methods from the entry-level class and actually row reduction. We'll do that another day. But finally, suppose, or next, look at if A is a square matrix, okay, how do we define A to the m exponent? Well, it's the matrix A multiplied by itself m times, and then if R and S are non-negative integers, we have the usual property of exponents, namely A to the R plus S equals A to the R times A to the S. And by definition, we define the square matrix A raised to the 0 exponent to be the identity matrix. The identity. All right? And then we have theorem 3.3, which says, very importantly, that the transpose of AB is transpose B times transpose A. Now, the proof is very intricate. Later on, when we do inner product spaces, we're going to have a 1 or 2 line proof of this. So I'm going to save it for later, and it will be a turn-in homework when we get in that chapter. But the transpose of the product is the product of the transposes in reverse order. And so that concludes our video for week number 4.